Somewhere beneath your feet, a jaw is cocked, spring-loaded, hair-triggered, locked open, and aimed at something that doesn't know it's already dead. That jaw closes faster than a bullet leaves a barrel, and it belongs to an animal you could crush with your thumb. Ants don't carry swords. They don't wear helmets. But over 150 million years, they've evolved weapons that close faster than you can think, and defenses so strange they grow rock armor out of their own skin, seal their nests with their own skulls, and neutralize nerve agents with chemicals they cook inside their own bodies. Human engineers still can't replicate any of it. You're crouched in a Costa Rican jungle, eye level with the dirt. Something the size of a coffee bean sits frozen in the leaf litter. Its jaws are locked open wider than its own head. They haven't moved in 30 seconds. This is the trap-jaw ant. A loaded crossbow packed into a body you could lose under your thumbnail. Those jaws snap shut at 145 miles per hour, faster than the fastest pitch ever thrown in baseball, and it happens in 0.13 milliseconds, 2,300 times faster than you can blink. The force behind that strike? 300 to 500 times the ant's own body weight. A human biting, with the same relative force, would generate over 60,000 pounds of pressure per square inch. But the jaw isn't just a weapon. It's an escape pod. When a predator gets too close, the trap jaw aims its head at the ground, fires its mandibles into the dirt, and the recoil launches it 20 body lengths backward through the air. Scaled up, that's you slamming your face into the pavement and backflipping 120 feet to safety. It built an ejection seat into its own skull. If the first strike doesn't kill, and it often does, slicing smaller insects clean in half, the ant doesn't wait for a second swing. It leaps onto the stunned prey and drives a venomous stinger into the body again and again until movement stops. A sniper, a guillotine, and a catapult, all in a package the size of a grain of rice. The trapjaw doesn't chase. It doesn't warn. It waits, and by the time you've triggered those hairs, it's already over. But raw speed is only one way to win a fight. The next species on this list doesn't hit hard. It paints its enemies with poison, and adjusts the dosage depending on who's receiving it. You're peeling bark off a dead log in the tropics. A swarm of tiny ants rushes out, and every single one flips its abdomen straight over its head like a scorpion about to strike. Meet the acrobat ant. Nature's chemical sniper with a built-in dosing dial. That raised abdomen is heart-shaped, literally, and it's loaded. The tip carries a modified spatula-shaped stinger that doesn't inject venom. It smears it, like a toxic paintbrush applied directly to the enemy's exoskeleton. And these ants control their dosage. When attacking a rival, they release 500 nanograms of venom, a weaponized blast. But when tending their own larvae, they secrete a single nanogram of the exact same chemical, using its secondary properties as an antibiotic to prevent fungal infections. Same compound, same gland. Weapon or medicine depends on who's receiving it. When they find prey larger than themselves, a wasp, for instance, they don't back down. Multiple workers swarm the target, pin its legs to the ground, and hold it spread eagle, while others methodically wipe venom across its face until it stops struggling. A pharmacist who moonlights as an assassin. The acrobat doesn't overpower, it calibrates. Precision chemistry is one thing. But there's a species in the Central American canopy whose weapon isn't calibrated at all. It's pure, unfiltered agony, and it only needs to sting you once. You're climbing a tree in the Nicaraguan rainforest. Your hand wraps around a branch. Something heavy, the size of your thumbnail, drives a spike into the webbing between your fingers. The world goes white. That's the bullet ant. A walking nerve grenade. It sits alone at the absolute peak of the Schmidt Pain Index, the scientific scale for measuring venom agony. A perfect 4.0 out of 4. The entomologist who built the index described it as pure, intense, brilliant pain, like walking over flaming charcoal with a 3-inch nail embedded in your heel. 100 fire ant stings register a 3.0. A single billet ant eclipses that entirely. The venom isn't designed to kill, it's designed to teach. The active compound, ponerotoxin, targets mammalian nerve receptors and floods the pain system with so much noise that the brain can't process anything else. 24 straight hours of burning. No fading. No relief. Just wave after wave. The predator that survives a billet ant sting will never touch one again. That's the entire strategy. And they don't travel in armies, they hunt alone. One ant, patrolling the canopy, carrying a sting potent enough to drop a grown human to their knees. No backup. No swarm. Just one body and the worst pain on the planet. 24 hours of agony from one sting. No wonder they're also called the 24-hour ant. The billet ant doesn't need an army, it just needs you to remember. But what if you could shrug off a chemical weapon designed to be lethal? What if your body could neutralize venom before it even reached your nervous system? There's one ant that can. And it figured out the antidote before any human chemist did. You're in a Houston backyard. The ground near the electrical panel is swarming. Thousands of ants, barely 2 millimeters long, running in every direction at once. No trails, no formation, just chaos. They call them Tawny crazy ants. And they've cracked the code to chemical immortality. Their rivals are red imported fire ants, one of the most feared invasive species on Earth. Fire ant venom packs piperidine alkaloids 2 to 3 times more toxic than DEET by weight. One sting kills most insects instantly. The crazy ant gets hit, stumbles, and does something no other insect on Earth has ever been recorded doing. It reaches back to its own abdomen, squeezes out a bead of formic acid, passes it to its mouth, and smears it over its entire body like chemical sunscreen. The acid neutralizes the fire ant's venom on contact. A crazy ant that completes this self-decontamination survives 98% of the time. It's the first and only insect ever documented to chemically detoxify another species' venom. They're also relentlessly self-destructive. When one worker gets electrocuted inside a breaker box, its dying body releases an alarm pheromone. Thousands rush in, they pile into the wiring, die by the hundreds, and the mound of fried corpses physically shorts out the entire system. They've disabled electrical grids and industrial equipment, all because of one dead ant's final chemical scream. Immune to nerve agents. Allergic to power outlets. The crazy ant doesn't outfight its enemy, it just refuses to die. Chemical warfare works when you can hit your target. But what happens when the battlefield itself wants to kill you? When the ground is hot enough to cook flesh and the air bakes your blood? One species runs straight into that. You're standing in the open Sahara at midday. Ground temperature, 60 degrees Celsius, nothing moves, nothing breathes. Except one thing, a speck, rocketing across the sand so fast it barely touches it. This is the Sahara desert ant, a biological heat shield with legs. It sprints at 80 body lengths per second. Scaled to a human, that's 400 miles per hour, and it moves so fast that all 6 legs leave the ground at once. It doesn't run across the sand. It gallops. A microscopic racehorse on a frying pan. That speed isn't just for escape, it's temperature regulation. The velocity generates localized air convection around its body, cooling it mid-stride. And when temperatures push past what any normal cell can survive, the ant activates specialized heat shock proteins that stabilize its cellular structure and repair degrading DNA in real time. It's running a biological maintenance crew while sprinting through a furnace. Its food? The baked corpses of insects that died from the heat. It forages during the deadliest hours of the day because nothing else is alive to compete with it. One navigational error means death by baking. It relies on polarized light patterns in the sky to calculate the exact, mathematically shortest vector back to its hole. Out here, geometry is the difference between lunch and a funeral. Meal plan, whatever died before you did. The desert ant doesn't dodge the danger, it outran evolution's kill switch. Speed saves you in the open, but in the canopy, where predators attack from above, you need a different kind of defense, the kind that makes eating you the worst decision a bird ever makes. You're brushing past a low branch in a Malaysian rainforest. Your finger grazes something metallic black. A sharp, immediate puncture. Not a sting, but something structural. Something small just impaled you. Meet the giant spiny ant, a walking strip of barbed wire. Its thorax and waist are covered in aggressively curved, razor-sharp spines, exoskeletal weapons specifically shaped to lodge deep in the throats of birds and lizards. It can't sting. It doesn't need to. Swallowing one is like choking on a fishhook. And while the attacker gags, the ant secretes liquid formic acid directly into the puncture wounds its own spines just created. Its nest-building method is where things get dark. Adults can't produce silk. So workers pick up their own larvae, living, unpupated grubs, and squeeze them gently in their jaws, moving them back and forth across leaf edges like hot glue guns. The larva produces silk on demand. The adults use it to sew leaves, bark, and debris into armored fortresses. The construction runs on child labor. And the colony wastes nothing. Injured workers that slow down are ripped apart by their sisters. The corpses get processed, compressed, and used as structural reinforcement in the outer walls of the nest. You serve the colony alive, or you serve it as building material. The colony is the HR department. The spiny ant doesn't just defend itself. It makes the cost of attacking higher than any predator is willing to pay. Spines work if the predator gets close. But what if you could calculate the exact moment to fight? and ignore every other threat until then. One species does exactly that, and the math is chillingly precise. You're watching a line of large, dark ants tending a cluster of tiny sap-sucking insects on a tree trunk in rural India. They stroke the bugs gently with their antennae. A ladybug approaches. The nearest ant doesn't react. Then the ladybug takes one step closer to the herd, and the ant attacks like a switch flipped. This is the Indian black ant. Nature's cost-benefit calculator with mandibles. Workers range from 6 to 13 millimeters, deeply grooved jaws, arched thorax, and a formic acid spray that works like a chemical fire hose. But the weapon isn't what makes it dangerous. The decision-making behind it is. Researchers tested this. When the ant is alone on a trail with nothing to protect, it mostly ignores threats. But station it next to a herd of honeydew producing tree hoppers, its living sugar supply, and it becomes 12 times more likely to attack. And it's nearly 4 times more likely to escalate to physical biting rather than just posturing. It doesn't just fight, it runs a real-time cost-benefit analysis on whether the asset it's guarding is worth dying for. When food runs scarce, the math flips. The same ants that fought to the death protecting their tree hopper herds will turn around and eat them. Loyalty lasts exactly as long as the economics support it. Wall Street with mandibles. The Indian black ant doesn't fight on instinct. It fights on calculation. Calculated violence is efficient. But what about overwhelming force? 500,000 soldiers who don't calculate at all because they don't need to. One colony turns the entire canopy into a militarized zone, and its weapon never lets go. You brush a leaf in a Thai mango orchard. Before you can pull your hand back, something locks onto your knuckle, hard, and a searing chemical burn blooms under the skin. You try to pull it off. It won't release. That's the Asian weaver ant. An acid-spraying siege engine that bites first, dies second, and never opens its jaws. Major workers pack 9.7 milligrams of formic acid per gram of body weight, a chemical payload that dwarfs anything in their size class. They bite deep into the skin with razor mandibles and simultaneously jet concentrated acid directly into the open wound. No stinger required. To build their fortresses, up to 150 nests spanning dozens of trees, workers form living chains. They bite onto each other's narrow waists and dangle in midair, creating biological suspension cables that physically pull stiff leaves across wide gaps. Other workers sew the seams shut using silk-producing larvae held in their jaws. A construction crew of 500,000 holding hands across the canopy. So effective that human farmers deploy these ants to protect mango, cashew, and cocoa crops from over 50 species of pests. In combat, major workers clamp onto a predator and refuse to release. Their body weight drops to 60% as they slowly starve. The ant dies. The jaws stay locked. The bite outlasts the body. Commitment issues? Not in this colony. The weaver doesn't defend a nest. It defends an empire, and it pays for it with bodies that were never meant to come home. Acid burns and locked jaws work above ground. But some ants don't rely on chemistry or muscle at all. They grow their own armor, and the material they use isn't chitin. It's rock. You're watching a line of ants haul leaf fragments into a tunnel in Panama. One of the older workers catches the light differently. Its exoskeleton doesn't shimmer like chitin. It glints like stone. This is the Spiny Leafcutter ant, the first insect ever discovered wearing biomineral body armor. Its shell is coated in thousands of microscopic crystals made of magnesium-rich calcite, the same mineral found in dolomite rock, the same material in sea urchin teeth, which are strong enough to grind through solid limestone. This crystalline layer makes its exoskeleton more than twice as hard as a normal ant's. The armor doesn't come standard. Young workers stay inside the nest, tending the fungus gardens with soft, uncoated cuticles. As they age and prepare to face the outside world, the colony's diet triggers massive crystal growth across their bodies. The longer they survive, the harder they get. It's age-activated armor plating, a geological promotion. This calcite shell didn't evolve against birds or lizards. It evolved for war, specifically against giant leafcutter ants whose jaws are built to shear through exoskeletons like scissors through paper. Without the mineral coating, a young spiny leafcutter gets cut in half on contact. And if a pupa gets separated from the colony before the armor grows, it never develops. That ant enters the battlefield naked. A mid-career upgrade that comes with a suit of rock. The spiny leafcutter doesn't carry a weapon. It becomes one. Growing your own armor is extreme, but there's a species that went further. It infused its jaws with raw metal, rebuilt its legs so they can never walk on flat ground, and sealed itself inside living wood forever. You're holding a branch that looks perfectly healthy, solid bark, green leaves. You snap it. The inside is hollow, crawling with pale, deformed ants that can't stand up on your palm. They writhe. They can't walk. They were never built to. This is the wood-boring ant, an organism that traded its ability to walk for a pair of zinc-reinforced drill bits. Its mandibles are biomineralized with elemental zinc, raw metal fused into the jaw to give it the hardness needed to chew through living, sap-filled hardwood. Its middle legs point straight up, the joints massively muscled and warped. They're designed to brace against the roof of a tunnel while the front end grinds forward. These ants physically cannot walk on a flat surface. Not slowly, not carefully. They can't do it. Their entire body is engineered for three-dimensional tunnel life. If they accidentally breach the bark, adults secrete silk to seal the hole immediately. Sunlight isn't a resource for this species. It's a structural failure. A single tree can host 1.5 million of these ants and 500,000 scale insects, all hidden beneath a layer of bark, slowly hollowing out the living vascular tissue from the inside. The tree looks healthy on the surface. Inside, it's a factory being eaten alive. They can't walk. They can't see. They've never touched grass. But they've consumed entire orchards. The wood-boring ant didn't adapt to its environment. It deleted every other option and became the environment. A species that can't walk is strange, but what if size itself was the weapon? If the difference between your smallest soldier and your largest was the difference between a mouse and a blue whale? You're watching a trail of ants in a Malaysian clearing. The tiny ones are barely visible, golden specks, 1.5 millimeters long. Then something rounds the corner. A soldier. Dark-headed. Square-jawed. 15 millimeters. 10 times larger than the workers currently riding on its back. This is the Marauder ant. A military factory with a 500-to-1 weight ratio between its smallest and largest soldiers. That ratio is one of the most extreme size gaps in nature. Scaled to humans, it's a 5-foot infantryman marching beside a teammate who stands 50 feet tall and weighs 75,000 pounds. The supermajors carry massive triangular mandibles that crush beetle shells and slice through arthropod armor like tinfoil. The tiny workers don't walk to the battlefield. They ride. They climb onto the heads and backs of the giants and hitchhike to the front lines. Once there, the micro-workers handle reconnaissance and trail maintenance, while the supermajors clear the path by force. The raiding columns stretch across the forest floor for hours without stopping. To keep this machine running, the queen operates as a biological munitions factory, laying thousands of eggs per day to replace casualties. The colony actively adjusts what size of worker it breeds based on what it's currently fighting. It doesn't just wage war. It manufactures the right army in real time. Dynamic staffing based on current battlefield conditions. Nature's defense contractor. The Marauder doesn't bring the right tool for the job. It builds the right tool from scratch every single day. But what happens when you scale that up, way up? When the army isn't thousands, but 20 million, and the soldiers aren't just strong, they're completely blind? You're lying in a tent in the Congolese rainforest at 3 in the morning. You hear something, a faint clicking, like rising static. Then the ground outside starts to move. They're called driver ants. 20 million blind mouths marching in a single column, consuming everything that can't outrun them. Their queens are the largest ants on Earth, up to 63 millimeters, nearly 2.5 inches. The soldiers' jaws are so powerful that the Maasai use them as surgical staples. They coax a soldier to bite a wound shut, snap off the body, and leave the locked jaws in place for days while the cut heals. 20 million workers. Every one of them blind. Every flanking maneuver, every river crossing, every coordinated assault executed through chemical signals alone. When they hit a gap, living workers link their bodies together, jaw to leg to jaw, forming bridges. The colony walks across their sisters' backs. Nobody volunteered. They eat earthworms, beetles, spiders, but the swarm doesn't discriminate. Tethered animals, injured snakes, anything that can't move gets stripped to bone. And if you try to pull a biting soldier off your skin, the ant's body rips in half before the jaws release. More personnel than every human military on Earth combined, and not one of them can see. The driver ant doesn't hunt. It erases. 20 million jaws, no eyes, no plan, and nothing in 100 million years has figured out how to stop it. Overwhelming force works in the open. But in tight spaces, in tunnels where the entrance is everything, one species solved the problem by becoming the entrance. You're examining a twig in a Florida mangrove. There's a small, circular knot in the wood, natural-looking, textured like bark. You press a fingernail against it. It moves. It steps backward into the darkness, and behind it, a tunnel full of activity. That wasn't a knot, that was a turtle ant, a soldier whose head evolved into a living door. The soldier cast has a completely flat, disc-shaped head, rimmed, armored, and sized to plug the entrance of a twig nest with sub-millimeter precision. When wedged in place, there's nothing for an attacker to grab. The ant tucks its antennae, mandibles, and eyes entirely beneath the rim of the shield. It doesn't look like an ant. It looks like wood. And it commits to the disguise. The head disc secretes a fibrous material from thousands of microscopic pores, building up a biological crust that blends perfectly with the surrounding bark. A predator staring at a plugged entrance doesn't see an ant. It sees a tree. A soldier's entire existence is this. Stand in a dark tunnel, face outward, for weeks. Don't eat unless a nestmate brings food. Don't move unless something attacks. And here's the cruelest part. A parasitic species called the mirror turtle ant has evolved to perfectly copy the host's body language and chemical signature. It slips past the living doors undetected and steals food from inside. Evolution spent millions of years building the perfect lock. Then it built the perfect key. The turtle ant doesn't fight, it seals. And when the walls hold, nothing gets in. When they don't, everything was for nothing. Armor, chemistry, living doors, every defense so far is about stopping the enemy from getting close. But what if the enemy is faster than anything you can see? What if the arms race isn't about strength at all, but about who fires first? You sift through a handful of jungle soil. Somewhere in that dirt, hiding among roots and fungal threads, is a predator smaller than a sesame seed, with jaws that fire faster than any resettable weapon in nature. This is the miniature trap-jaw ant, a microscopic crossbow with a world record. Its mandibles use a system called latch-mediated spring actuation. Internal muscles slowly deform the exoskeleton, storing elastic energy behind a tiny biological latch. When the latch slips, the jaw fires at an acceleration 6 to 7 orders of magnitude beyond normal muscle contraction. It bypasses the physical speed limit of living tissue. This mechanism evolved independently 7 to 10 separate times within a single genus, Strumigenus. Minor structural tweaks to the mouthparts unlocked explosive, spring-loaded power and triggered a massive radiation of skull shapes across over 900 species. Evolution didn't build this weapon once. It kept rebuilding it, because nothing else worked. The target? Springtails, tiny soil creatures carrying their own spring-loaded catapult, an abdominal latch that launches them out of danger in milliseconds. The miniature trapjaw had to evolve the fastest resettable jaws on the planet, because its lunch was already rocket-powered. And when something bigger threatens the ant, it plays dead. Total freeze. Reserves the weapon strictly for hunting. World record jaws and an Oscar-worthy death scene. Range. The miniature trapjaw didn't win its arms race by getting bigger. It won by getting faster, 900 times over. 900 species share one limitation: their jaws open outward. What happens when there's no room for that? When you're hunting in tunnels so tight a standard trapjaw can't deploy? One species solved it with a completely different mechanism, and broke every speed record in the animal kingdom. You're digging through leaf litter in a Cambodian forest. 5 centimeters down, in total darkness, something the weight of a dust mote just switched off a centipede's nervous system. You didn't see it happen. Nobody could. This is the Dracula ant. The fastest strike in the animal kingdom, powered by a finger snap. Its mandibles don't swing open and shut. They press together, tip against tip, until the internal structure deforms under the strain. Then one slips past the other in a violent, instantaneous release, exactly like snapping your fingers. The result? Acceleration exceeding 1 million times the force of gravity. 90 meters per second. 200 miles per hour. In a fraction of a millisecond, the fastest self-powered movement ever recorded in any living organism. The mechanism exists because of real estate. Underground tunnels are tight. A traditional trapjaw needs room to swing open wide. So evolution built a weapon that generates maximum force with zero wind-up space. No arc. No opening. Compression and release. If a human could punch with this acceleration, their fist would reach 200 miles per hour in 15 millionths of a second. The bones in their arm would vaporize before they made contact. The name is earned. Adult Dracula ants can't digest solid food. They feed prey to their larvae, then chew holes into the larvae's skin and drink their hemolymph, their blood. Non-lethal. Repeated. The children are living blood banks the colony drains on schedule. The fastest punch on Earth, delivered by a species that feeds on its own kids. Nature's Ursum gets stranger every page. The Dracula ant doesn't need room to strike. It doesn't need venom. It needs contact and 1/1,000,000th of a second. Speed. Acid. Armor. Zinc teeth. Living doors. Every weapon so far costs something. Time, energy, mobility. But there's one species that pays the highest price of all. Its weapon works once, and using it is the last thing it ever does. You're 40 meters up in a Borneo dipterocarp tree. The canopy hums with territorial skirmishes. A rival ant, bigger, armored, crosses into the wrong patch of bark. A tiny worker, half its size, rushes forward. It wraps its legs around the intruder. Locks on. Then its abdomen starts to swell. This is the exploding ant. Nature's biological suicide bomber. Its mandibular glands don't sit in its head. They run the entire length of its body, from skull to abdomen, bloated with a bright yellow, highly toxic, corrosive adhesive. When a threat arrives, the minor worker doesn't sting. It doesn't bite. It contracts its abdominal muscles so violently that its own exoskeleton ruptures. The body tears itself open. The yellow fluid sprays outward, coating the attacker in a chemical that's simultaneously poisonous, corrosive, and sticky enough to harden into a permanent seal. The attacker suffocates. Its joints lock. Its exoskeleton dissolves where the fluid touches. Two insects die together, fused in a hardened chemical embrace. This isn't a last resort. These workers actively seek out invaders. They wrap their legs around the enemy first, ensuring maximum payload delivery, and then detonate. Preemptive. Deliberate. A weapon designed around the certainty that the user won't survive. The math is clean. A sterile worker carries 0 genetic value. The queen carries all of it. One worker's death, converted into a chemical bomb that removes a direct threat to the colony's reproductive future, that's not sacrifice. It's accounting. 150 million years of evolution, and the most effective weapon on Earth isn't a jaw. It isn't a sting. It isn't venom or armor or speed. It's a worker who was never going to reproduce, choosing to become a weapon so the colony doesn't have to lose one that matters. And that's the thing about ant weapons. Trapjaws snap. Bullet ants burn. Weavers lock on and never let go. Drivers erase. Dracula ants strike faster than any living thing on record. But the exploding ant doesn't outrun you. It doesn't outbite you. It doesn't outlast you. It just erases itself and takes you with it. Because every weapon on this list, every jaw, every acid gland, every suit of rock armor, every pair of zinc drill bits, evolved for the same reason. Not to protect the ant. To protect the colony. The individual was never the point. It was always the expenditure. And in a world where one queen carries all the future and 10 million workers carry none, the deadliest weapon isn't the one that hurts the most. It's the one attached to something willing to disappear.